Since Sonic the Hedgehog arrived on the C64, memory expansions finally seem to have full visibility on the C64. But as a basic programmer, this additional RAM is not for you, they say. You're stuck with whatever basic bytes free. For me, memory expansions are maybe the most exciting way to beef up your 8-bit computer, and there is no reason you shouldn't use them, even in basic programs. In this video, I'll show you how to go beyond the limits of basic bytes free and how you can apply this to your project. Welcome to the 8-bit theory. I'll cover the GeoRAM and the REU for the Commodore 64 and 128. I'll also cover the X16 and the Mega65. These don't support memory expansions, but they come with way more built-in RAM than regular BASIC can chew. REUs were built by Commodore and CMD, and these go from 128 kilobytes to up to 2 megabytes. GeoRAM starts at 512 kilobytes and I think was also available up to 4 megabytes. On the X16 we also have 512 kilobytes and we have at least 384 kilobytes on the Mega65, including the Nexus boards. Regular Mega65 boards come with an additional 8 megabytes of attic RAM. Before going into the use cases, I'll introduce you to working with raw data. You'll need to be okay with going beyond the trusted safe space of basic variables and be ready to enter the world of raw bytes, peeks and pokes. Let's take the memory map of the C64 as an example. Basic memory spans from address 2048 to address 40,960. And only this area can be used by the basic interpreter for lines of program code and for variables. But looking at the memory map, at 49,152, we have another 4 kilobytes of free memory. And poking a certain value to 49,152 allows me to get back that same value via peek. That means through peek and poke, we can also use the memory areas that are beyond the basic memory area, but only for values between 0 and 255. As a showcase, I would like to show how to copy and retrieve data from the screen to extended memory, and as every character on screen is represented by a value in that range, we should be good to go. Now on to storing screen data in expanded memory. Of course, it depends on the type of game whether storing and restoring screens in expanded memory makes sense. But for one, it helps me to visualize what we are doing, and for another, this involves working with color RAM, which requires a little bit of extra handling in terms of I/O. With that being said, anything that works for screen data usually works for any kind of data, so feel free to experiment. All the code shown and more is available on GitHub. Let's look at the GeoRAM first. It is connected to the expansion board and directly maps 256 bytes of its own memory into the C64's memory space. 256 bytes are referred to as one page. In the GeoRAM, pages live in banks, which are 16 kilobytes in size. The total number of banks add up to the memory expansion's total size. Any value that's written to the mapped memory area is actually directly written to the GeoRAM's memory according to the selected page and bank. The C64's memory is left untouched. I created a test program that prints to the screen and it also measures the time this takes. Printing a full screen takes about 32 jiffys, that's about half a second, as we can see on the top left-hand side. The screen contents are copied to the GeoRAM. Once printing is done, pressing a key clears the screen. Another key press copies the screen contents from the GeoRAM back to the screen, and this took 24 jiffys. How does this test program work? Copying 1000 bytes in BASIC by running through a for loop that does 1000 peeks from screen memory and 1000 pokes to extended memory would take very long. Much longer than just 44 jiffys. Lucky us, there's a kernel routine that allows us to copy up to 256 bytes at once, and this was documented years ago on Forum 64 by user GoDot. I'll put a link to his projects in the description. That routine is directly working with memory addresses, of course not basic variables, so we need a source address, a target address, and the amount of data that's to be copied. For the source address, we do know the memory address of the screen. Per default, this is at 1024 decimal, which is hex 400. For the amount of data, we also know that the screen is always 40 by 25 characters in size, which is 1000 bytes. We can transfer a maximum of 256 bytes at once to and from GeoRAM memory, which is the maximum amount of data. So we will need 4 copy operations per screen, a huge improvement over 1000 copy operations. We also know the address of the 256 bytes memory window of the GeoRAM, which is the target address. So for working with full screen contents, we know everything we need to be able to use the kernel routine for copying to GeoRAM. And this is the test program. After printing and calculating the duration, the contents are copied to the GeoRAM. You see a loop with 4 iterations. The first goes up deals with storing screen RAM, the second one with storing color RAM. After that comes checking for key presses and calling the restore subroutines. Again, one for the color RAM, one for the screen RAM. And here's the program running again. It's very apparent that 4 copy operations are required for the full screen, 8 really when also counting color RAM. What do you think? Why did I restore color RAM before restoring screen RAM? Let's just look at it the other way. When running this, it looks as if each section was drawn twice, so that's why it's better to do it the other way around. Set the color when no characters are present, and once characters are set, the color is already correct. So for using the GeoRAM, we need to issue poke commands to set the parameters. Executing the copy operation is done through a kernel syscall. Restoring the screen takes 24 jiffies. We will see how the other options perform. Next, let's have a look at the REU, and the concept is fundamentally different to the one of the GeoRAM. Data is not directly written to the REU's memory. Instead, data is copied between the computer's memory and the REU's memory. That sounds cumbersome, but it's so fast that usually you won't recognize any interruption by doing it. Reason for the high speed is the rack chip inside of the REU. The rack chip takes over control of the computer when copying, directly accessing RAM, bypassing the CPU. DMA is the magic word, and that's short for direct memory access. The REU has memory banks of 64 kilobytes. Once a bank is selected, you are free to copy contents from that bank between the computer and the REU. The amount of data can be as small as 1 byte or as large as the full 64 kilobytes. And this is how the REU setup is done. The base address is 57,088. This allows access to the necessary registers on the rack chip. Registers 2 and 3 set the memory address on the computer side. Registers 4 and 5 define the memory area of the REU's current bank. Register 6 selects the REU bank. Registers 7 and 8 define low and high byte of the amount of data to be copied, up to a total of 64 kilobytes. And finally register 1. This is an interesting one. There's a couple of flags that can be set, but I will only cover the relevant details. The lowest 2 bits set the transaction type, 0 or 1 in our case, for writing to or reading from the REU. Next interesting bit is bit 4. This also needs to be set for our purpose, which adds decimal 16. And then the highest bit set suddenly means that by writing to this register, we want to trigger execution. That adds another 128. So to stash data in the REU, we write the value 144 to register 1. To fetch data from the REU, we write value 145 to register 1. Like in the previous test program, a key press clears the screen and a subsequent key press recreates the screen from REU data. Print takes about 30 jiffies in this program to build a full screen. The REU does it in 11 jiffies, and that is for screen RAM and for color RAM. We can see color and screen RAM being copied in sequence again, but now it's only 1 copy operation instead of 4. And this is how it looks when we copy color RAM before we copy screen RAM. Just like with the GeoRAM, the pokes look a bit cumbersome, but that's not as bad as it seems. In contrast to the GeoRAM, only poke commands are required, no sys. With 7 jiffies, the REU takes the lead. And before we move on to the Mega65's Go64 mode, we should check how the 128 does REU. Basic 7 on the Commodore 128 brings basic commands for fetch, stash and swap on the REU. We still have to deal with memory addresses instead of variables, but at least calculating low and high bytes becomes a thing of the past. As we can see in the Basic 7 port of our test program, a lot less code is required than for the peek and poke approach on the C64. What used to be a full code block is now a single line of code. Very important detail, copying screen RAM is done from bank 0, while we switch to bank 15 to copy from and to color RAM. Color RAM is stored in a dedicated memory chip, so we need to have I/O mapping enabled, which is the case in bank 15. Let's run this. On the C128, print is only half as fast as on the C64. That's because the basic interpreter is slower at 1 MHz due to banking between banks 0 and 1, and maybe for more reasons. But in turn, stash and fetch are a lot faster. Copying screen RAM and color RAM only takes 2 jiffies. And we can do all that by just using basic commands. Now, on to the Mega65's Go64 mode. This mode is not what Go64 mode on the C128 is. I did a video about that difference. If you're interested in an overview, feel free to check that out. In Go64 mode on the Mega65, you can also enable access to all the enhanced Mega65 features easily. One of these is DMA, and you can use that to take advantage of the large amount of memory the Mega65 comes with. RAM is divided into 2 flavors, 384 kilobytes within the first megabyte of memory and 8 megabytes of attic RAM located at address hex 8 million. Nexus boards only come with 384 kilobytes. All regular Mega65 revisions come with attic RAM on top of that. Access to the first 384 kilobytes can be done through standard DMA, which is quite simple to use. Basic 10 had the DMA command for that, so Basic 65 also has it. And there is extended DMA, which can access all the RAM, the 8 megabytes of attic RAM, but also the first 384 kilobytes. For that, the eDMA command was introduced in Basic 65. In Go64 mode, we only have Basic 2 without these commands, but as it is good tradition on the C64, we can always use poke to achieve what DMA and eDMA do. Here's how the standard DMA approach works with pokes. In Go64 mode, you can fully use bank 1 and its 64 kilobytes of RAM, and when only working with VIC2 features, banks 4 and 5 are also fully available for you to use. You could even use bank 3 as that holds the C65 ROMs, but this bank is write protected by default, which we need to disable before using. So 256 kilobytes of RAM are usable in Go64 mode with the standard DMA commands without running into any conflicts. Basic DMA commands are executed by a DMA chip, just like the REU has one. But the setup is different. First, you'll need to activate the DMA registers because these are not active in Go64 mode per default. It tries to mimic a real C64 after all. This is done by sending 2 poke commands. See the video about the Mega65's I/O personalities for more details. Instead of setting all register values accordingly each single time, we can store the full command set into memory. These command sets are called DMA lists. For standard DMA, a command set is 12 bytes long. Byte 0 contains the type of command. As of today, only copy and fill are supported. Byte 1 and 2 describe the amount of data to copy. Byte 3 and 4 contain source address, low byte and high byte. Byte 5 is source bank and flags, and we will come to that in a second. Bytes 6 and 7 are destination address, low and high bytes. Byte 8 is the destination address bank and flags. Bytes 9 to 11 are 0 for our purpose. Now we store these values to a certain memory address, and we create one command for copying screen RAM to a different bank and one for retrieving screen RAM from that bank. and 2 more commands for storing and recovering color RAM. The bank and flag byte is interesting. Bits 0 to 3 cover the bank, which allows for 16 possible values. We won't use hold, modulo, or direction here, but we will need to use the I/O flag when we copy color RAM. And the reason is the same as on the C64 when we used bank 15 for the REU. The I/O ports need to be mapped so that whatever we write goes into color RAM. I used strings in the test program to just assemble these DMA lists, and I poked them to a certain address with an offset of 12 bytes each. When we want to execute the DMA function, we store bank, high byte and low byte of the DMA list into 5542 to 55040. 55040 not only sets the low byte, it also triggers execution of the DMA operation. As you can see, this is pretty fast, just 5 jiffys. The REU took 11 jiffys for this. The fact that we are able to fully prepare the DMA lists so that only 3 pokes are required makes the significant difference. Only peek and poke are required for the Mega65's Go64 mode with DMA. If you prefer basic commands, you can use native Basic65. And I'll show eDMA here real quick. You see, there is next to no code required. It is just as convenient as the REU commands on the C128. We still have to copy screen RAM and color RAM separately, but we can work with large address values here. No need for low byte, high byte calculations. The eDMA command takes 4 parameters. Again, command is 0 for copy, length of data is 2 bytes, source can be an 28-bit address and the target address as well. We will store 1024 bytes, which is 400 hex, from hex 800, which is the location of screen RAM, to hex 8 million, that's the start of attic RAM. And another 1024 bytes from hex FF80000, which is where color RAM is stored natively, to hex 8 million plus 400 hex. Basic65 shows time in seconds, not in jiffys. And of course, this is really fast and still very important to notice, in my opinion. Filling the screen via DMA is still orders of magnitude faster than printing to the screen. Just like on the C128, we can work with only basic commands, and DMA is so fast it takes just a fraction of a jiffy to build the screen. The last system we'll cover is the X16, which is exciting because it's a little bit different to the Commodores. On the X16, extended memory is directly mapped into the accessible memory range. That's like what the GeoRAM did, with the difference that it's not just 256 bytes that are available from the computer's perspective, but 8 kilobytes that we can directly work with. The area that's used for that is 40,960 to 49,151, which is hex 8000 to hex BFFF. And here as well, basic variables cannot make use of this area. But as on the C64, we can use a kernel routine to copy a larger number of bytes. On the X16, that's the dedicated memory copy function, which is well documented and lives at 65,255 or hex FEE7. And this is how the function works. The R parameters describe 0-page locations, and this is how all the kernel functions on the X16 are documented. R0 refers to addresses 2 and 3, R1 to 4 and 5, R2 to 6 and 7, so each one describes a 16-bit parameter. And we're familiar with the parameters: source address, target address, and number of bytes to copy. Okay, we just need the address of the video RAM and we're good, right? Well, here's where the X16 is different. The Vera chip has dedicated VRAM, so we can't directly access that like on the previous platforms. And for single peeks and pokes, this is not a problem because the vpoke and vpeek commands accommodate for that. But we would like to copy a couple thousand bytes at once, which is why we need to go a level lower. Luckily, the designers of the memory copy routine I just mentioned kept that in mind. To communicate with the Vera, the X16 provides a couple I/O addresses we can work with. Addresses hex 9F20 and hex 9F21 contain low and high byte of the VRAM address we want to work with. That allows to address 64 kilobytes. But as we have 128 kilobytes of VRAM, the lowest bit in hex 9F22 allows us to switch between the lower and the upper 64K of VRAM. We'll also need to set the lowest bit of hex 9F25 to 0, and I will tell you in a minute what this is for. Looking at the Vera memory map, we see that text mode starts at bank 1 B1000. So a vpoke to 1, hex B1000, 1 is similar to poke 1024, 1 on the C64 and puts an A to the top left corner. Vpoke 1, B1001, 3 should then write a C to the second position, right? Because hex B1001 is the second text cell and 3 must be the C. But look, it renders the first character in a different color. Color RAM is handled differently by the X16's Vera chip. It's always 2 bytes per character. First byte is the character's screen code, second byte is the color information. That means we do not have to do 2 dedicated copy operations, one for screen RAM and one for color RAM. We can just copy 2400 bytes and we're good. Okay, how should we tell that memory copy function to copy to VRAM instead of RAM? We have written our target address to hex 9F20 and 21. Now, if we specify hex 9F23 as the target address, the memory copy function is smart enough to know that this means we want to copy to VRAM. And it's also smart enough to know where to take the VRAM target address from. And the same goes for copying from VRAM. We just use hex 9F23 as source address. So this is the setup to copy between VRAM and RAM. Print takes 4 jiffies on the X16 and restoring via memory copy just takes 1 jiffy. We already learned that the Vera comes with 128 kilobytes of VRAM. For a 40 by 30 screen, we only need about 2400 bytes, also taking color RAM into account. Can we not use that surplus of VRAM to keep copies of the screens in memory? For that, both the pointers to source and target address need to point to VRAM. How does that work? Remember that 0 value from hex 9F25, where I said we'll cover that later? We'll cover that now. We have 2 pointers into VRAM called data port 0 and data port 1. So far we worked only with data port 0. And we can use data port 1 as a second pointer to VRAM. To do that, we have to first set the lowest bit of hex 9F25 to 1 for data port 1. Then we write the VRAM address again to 9F20 and 9F21. We also set the VRAM bank to 1 again, just in case the register was changed in the meantime. And that's a very important thing to remember actually. Whenever working with machine language from BASIC, always set the register values because some basic commands that were issued in the meantime could have changed these again. Also, after writing the address into data port 1, we will need to switch hex 9F25 back to 0. Why? Because BASIC expects this value to be 0. I ran into trouble when trying this because I wasn't aware of that, and while working with data port 0 worked perfectly fine, data port 1 didn't, because I left that register value to 1. People on Discord helped me out there, thanks a lot for that. Back to our setup, just as we use hex 9F23 to tell the memory copy function to use the address from data port 0, we can now use hex 9F24 to do the same for data port 1. When we run this, the speed is identical to the previous version where we copied between VRAM and RAM, but with this approach, no regular RAM is used. This way, no banking for display purposes is required, which might be beneficial. Okay, and here's a summary of what we had. We see three different concepts of using expanded memory. GeoRAM and the X16 provide kernel functions for CPU-based copying of the data. They have in common that parameters are set via peak and execution is triggered through a kernel call. By the way, GeoRAM works on the 128 exactly the same way as on the C64. Then we have the DMA approaches. That's the REU and the Mega65 implementations. They have in common that only pokes are required, and this includes triggering the execution of the data copy. Last but not least, direct basic support. This is the most convenient to use. Of course, you could also use poke on these platforms, but why would you? While the GeoRAM only leaves an average impression, there's definitely some advantages to it. The price point of original hardware for one. The REU was always more expensive than the GeoRAM and still is today. With the rack chip not being available anymore, there is no replicas available. The GeoRAM, on the other hand, you can even build yourself. If you decide to enrich your projects by using expanded memory, let me know in the comments. All files shown in this video are available for download from the link in the description. If you like this content, please subscribe to this channel, enable notifications, and make sure to check out my other videos. Thanks for watching. See you next time at the 8-bit theory, obsolete but not useless.